Uttam Prabha. Digital India. Educated India.
Dear students, I welcome you all to the 6th lecture on crystallography. If you remember, in the last 5 lectures, we have studied the points group of symmetry and we have studied 32 point groups of symmetry, and we have classified them into 7 crystal systems, and we have discussed in some detail the classifying criteria of these point groups of symmetry in the 7 crystal systems. Today, we will study a new topic that is on translational symmetry, and we will define this translational symmetry, and we will study 2 types of plane lattices. One variety of plane lattices is the 2-dimensional plane lattices, and the second type of lattices we call it as 3-dimensional or Bravis lattices here. So, what is a translational symmetry here? In translational symmetry, what happens here is that lattice nodes are translated in a particular direction along a repeat vector, as has been shown here, and this particular translation along a particular direction along a particular repeat vector develops an one-dimensional array of lattice points here, and this we call it as a row. Before going to the next stage, let us discuss about the lattice here. Lattice is a periodic array of points where each point is indistinguishable from any other points and has identical surroundings here. So, what happens here is that in case of translational symmetry along a particular direction, the periodic translation along a particular direction will develop a pattern here, and this pattern along one direction we call it as a row. If this row is translated along a second direction, that is the b direction, and with this repeat distance is around b unit, then we develop a 2-dimensional geometry of this lattice points here, and this particular pattern we call it as a net. Now, in this net you have the smallest repetitive volume of the crystal. This is the, if this is the smallest repetitive volume of the crystal, then we call it as a unit cell. Why unit cell? Because this unit cell or this smallest volume, when stacked together with replication, reproduces the whole crystal here. In this case, the unit cell is studied by translation only, and that generates the entire pattern here. Now, one of the important aspects of translational symmetry is that lattice points, and here these are the lattice points here, and this is also the motifs here. They can also be linked with the point groups of symmetry here. Now, this is, if you see here, this is 6, this is translated along this direction here, and this is the periodicity, this repeat distance is, say, this is a, and say for example, if you have a two-fold axis symmetry or dyad here, and then 6 is rotated 180 degree, and it produces another motif here, say it will be look like 9, and this will be translated along the same a unit along the same a direction, and it will produce this pattern here 9, and this pattern 6 and 9 can be translated along this direction, and we develop the whole 2-dimensional geometry of this crystal here, and this lattice nodes and the point groups of symmetry are interlinked. Okay. Apart from this kind of simple translation along a particular direction, we also learn a new type of symmetry operation where a translation is combined with reflection here. So, let us consider that you have a motif called 6, and if there is a mirror plane along this orientation, and what happens here is that this after reflection generates an image this, and if it is translated along a distance which is half of the total distance between this 6 and this 6 here, and I will show you shortly. So, then it generates a new point here, and reflection plus translation to the half of the distance here, and another set of reflection, this produces again 6 here, and it is translated along this direction, and this direction is half of the distance between this 6 and 6 here, and it produces a pattern 6 here, the inverted image of 6, but at a location here, and another motif of 6 here. So, this 6 and this inverted image of this 6 here, they are transient positions and they can be ignored. So, essentially the pattern that is developed here is 6 here, and this is this inverted image of 6 here and this normal image of 6 here. So, this periodicity of that developed due to combined reflection and translation, this operation is called glide operation here, and this plane is called a glide plane. Now, this kind of symmetry operations, the translational symmetry operations, can be linked with 10 fundamental types of point groups of symmetry, which are of two dimensional nature here. What are those 10 different types of two dimensional point groups of symmetry, which we have studied in previous lectures? They are 1, 2, 3, 4, 6 m, 2 mm, 3 m, 4 mm and 6 mm. And the nature of translation and that in the two dimension and their unit cell lengths and the angle between the two directions, that result in 5 different types of lattices. And what these 5 different types of lattices? We call it as number 1, we call it as oblique or parallelogram type of lattice. And how this is generated? This is generated when A is not equal to B and the angle between A and B is not equal to 90 degree. The second type of plane lattices which is called rectangular plane lattices here, where A is not equal to B and the angle between A and B is 90 degree. The third type of plane lattice is called square type of plane lattice, where A is equal to B and the angle between A and B is 90 degree. The fourth type of square lattice is called centered rectangular or diamond type of lattice, where A is not equal to B and the angle between A and B is equal to 90 degree. And the fifth type of plane lattice is called rhombic or hexagonal type, where A is equal to B and the angle between A and B is equal to 120 degree. When these points group of symmetry are combined with these 5 types of lattices, they generate 7 type of plane groups here. We call it as two dimensional lattices here, 2 dimensional space groups. They are 17 types of planar 2 dimensional space groups. Let us see in some more details about these 5 types of subdivisions of the 2 dimensional plane lattices here. This is the one which we call it as square lattice. This is the unit cell of a square lattice, where A is equal to B and the angle between A and B is 90 degree. This is the one where you have, if this is the hexagon here, this is 1/3 part of that is this particular domain here. This particular part is called this we have studied here as a rhombic or hexagonal plane lattice, and A is equal to B, and this angle is 120 degree here. And you have a this type of lattice here where A is not equal to B and this angle is 90 degree. We call it simply rectangular plane lattices here. And you have this most common type of two dimensional lattices here, where A is not equal to B and also the angle between A and B is not equal to 90 degree. We call this as oblique lattice, also we call it as parallelogram. Now, we have the fifth type of lattice, we call it as centered rectangular type of lattice. In the centered rectangular type of lattice, what we have here, if this is a rectangle, apart from the lattice nodes lying at the four corners, you also have a lattice node at the center of this particular rectangle here. Question is how this can be formed? This can be formed in such a way, you have, let us consider this is the direction of translation along A direction here, and the total amount of repeat or unition. The term primitive is used here for a lattice, where lattice nodes for a unit cell lies at the four corners here. Now, what is the effective total lattice for such a situation here for primitive lattices here? This will be 1. Why? Each unit cell is surrounded by 4 such unit cell from 4 sides here. So, if you have, then what you have here? The effective sharing of a particular lattice node here is 1/4. So, 4 into 1/4 is equal to 1. So, you have the lattice points for this particular type of primitive lattice is equal to 1. Whereas, in this kind of centered rectangular type of lattices here, you have the lattice nodes at the four corners, that is effectively one lattice point, and you have also have a lattice point at the center of the rectangle, which is unshared. So, total lattice points in a centered rectangular lattice we have 2. So, in case of centered rectangular lattice, the effective lattice point is 2. In case of primitive one, you have lattice point is effective lattice point is 1. Now, what are the 10 point groups of symmetry which can be combined with this particular 5 types of two dimensional lattices here? So, they are one-fold axisymmetry, two-fold axisymmetry, you have mirror plane, you have 2 mm, you have 4 and you have 4 mm, and you have three-fold axisymmetry, you have 3 m combination, you have 6-fold axisymmetry and 6 mm. So, there are a total of 10 point groups of symmetry. All point groups of symmetry cannot be combined with all the two dimensional lattices type. So, what you have to do is that they will be linked with only specific types of two dimensional lattices here. When we talk about the oblique lattice here, the point groups of symmetry that are combined here, they are either one-fold axisymmetry or two-fold axisymmetry here, and the lattice is primitive. And if you want to name the two dimensional lattice which will link with the point groups of symmetry, we call this as space group, and we call it as P 1 and P 2, where P is the primitive lattice type and 1 and 2 they refer to the types of point groups of symmetry. This is one-fold axisymmetry and this is two-fold axisymmetry here. In case of rectangular plane lattice, we have 2 types of point groups of symmetry which can be combined with this. What they are? They are 1 m, that is simple mirror, and you have 2 mm. So, you remember 2 mm, what is that? You have a vertical two-fold axisymmetry and you have two vertical mirror planes. They are at an angle of 90 degree to each other. That means, the two vertical mirror planes, they intersect along this vertical two-fold axisymmetry. And if you have the primitive type of lattice here, so then P will be combined with M. So, you have a space group, two dimensional space group, which is P M, and you also have P combined with, say for example, primitive lattice combined with 2 mm. So, you can also have P 2 mm, and also you can also have a simple glide plane that can be combined with the primitive lattice here. So, the symbol then will be P G, and in this case you have a two-fold axisymmetry, that is vertical, you have a simple mirror plane, and you have perpendicular to the mirror plane, you have a glide plane. That combination will be given a symbol P 2 M G. And finally, you can also have simple rectangular two dimensional lattice. You also have a situation where you have a two-fold axisymmetry, that is vertical, and you have two glide planes at orthogonal relationship here, and we call this as a symbol is P 2 G G. In case of centered rectangular plane lattice, what you have here, C combines with simple M and C combines with this 2 mm here. So, in this case, in case of centered rectangular lattice, you have a space group which is C m and the other is called C 2 mm. Let us now come to the square lattice, square plane lattice. In this case, as we have seen, A is equal to B and gamma is not is equal to 90 degree. So, we have two point groups of symmetry which can be present with the square lattice. One is simple four-fold axisymmetry and the other is 4 mm. And you have only primitive lattice here. So, P combines with 4. So, we have simple P 4, P combines with 4 mm, we have P 4 mm, and you have a combination where primitive lattice can combine with a vertical four-fold axisymmetry, and you have two sets of orientation. One set is mirror plane is present, they are two in number, and you have also has a glide plane here. So, you have a glide plane and also has a mirror plane here. And in case of hexagonal two dimensional lattice, where A is equal to B and gamma is equal to 120 degree, there are four possible point groups of symmetry which can be combined with this kind of plane lattices here. And what you have here, the primitive type of lattice can be combined with 3. So, we call it as P 3, and P can also be combined with 3 m combination, but how this translational symmetry direction is related to the directions of orientation of mirror planes, you can have two separate types of combination. One we call it as P 31 m or P 3 m 1, where 1 essentially refers to the position where the mirror plane and the direction of translation, their angular orientation is meant. I will discuss this shortly. And then you have this combination here when you have a vertical 6-fold axisymmetry. So, you have a combination of P 6 and you have a P 6 mm. So, let us now show you certain diagrams where it will be possible for you to appreciate this, how many types of space groups are generated here. So, if you can count here. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So, you have 17 types of space groups that have been developed by these combinations of 5 two-dimensional lattices with 10 types of point groups of symmetry. And let us show this with respect to this particular motif here. So, this is a dinosaur here and this is a very simple one P 1. So, this is you know that P 1 is for an oblique lattice where you have a parallelogram type of feature. So, it is translated along this A and along this B, and the A is not equal to B and this angle is not 90 degree. So, this is essentially develops a very simple this kind of P 1 arrangement here. So, the space lattice is something of this orientation here. So, let us now come to this particular arrangement here. So, what we have here? So, let us consider this is the dinosaur here and let us consider the presence of a two-fold axis of symmetry here. So, what will happen here? This vertical two-fold axis will act on this particular the first dinosaur here and will generate in another dinosaur of this orientation here. So, what happens here? This pair now can be translated along this direction and along this direction this A and B, this repeat units they are unequal and the angle between A and B direction that is not equal to 90 degree. Now, let us come to this third type here, we call it as P M type here. So, this is where this comes in the rectangular plane lattice here. What you have here? Let us consider that you have in this case when you have P M you have a single mirror plane here. So, if this is the orientation of this dinosaur here, if you have a mirror plane of this orientation here. So, this dinosaur in this row will be reflected and will generate another row here of this inverted image of this dinosaur here. So, this particular pair will now be translated along this direction along A direction and you can also translate this pair along this direction here and the angle between these two is 90 degree. What you generate here is a P M type of space group that comes under the rectangular plane lattice here, because this is a rectangle here. Then you have a situation where you have this particular part here, you can think of this you start with this dinosaur here and you orient a mirror plane of this orientation here. So, if you have a mirror plane of this orientation, immediately this dinosaur after reflection will produce this dinosaur here. And if you also orient another mirror plane of this orientation here, what will happen? So, this dinosaur and this dinosaur will be reflected and will develop another two dinosaur here. And the intersection of this mirror plane and this mirror plane at 90 degree, you know, it will generate a two-fold axis symmetry which will be vertical. Immediately you can relate this dinosaur with this dinosaur with a 180 degree rotation here. So, once you generate this particular grouping and then you can translate along this direction along A direction. So, that means, if you have the center here you come here. So, this 4 dinosaur unit can be translated along this and also can be translated along this, and this distance is B, this distance A, this is not A is equal to B, and you have a rectangular plane lattice here, and this has generated because of this combination of primitive lattice and also the 2 mm point group of symmetry under the rectangular plane lattice group here. Now, let us come this centered M. So, that comes under centered rectangular type of plane lattice here. So, what you have here immediately you can remember this is the dinosaur here. So, if you have a mirror plane of this orientation here. So, what you have here is that you have this particular part here is that this is after reflection, this generates this particular part here. And if you have this particular part, if you have this, and you can also have this particular translation, you generate this particular pattern, and then if you can translate this along this direction of B in such a way if this is the B unit length, then the twice of B is somewhere here, and the angle between A and 2B, if we take it as theta. So, cos theta is equal to A by 2B. If you have that, then you generate this rectangular centered rectangular lattice, and within that you combine this mirror plane here. Now, if you have a 2 mm situation here, just like this, what you have here P 2 mm, but the difference between these two is that you have between this rectangle, you have the center, this 4 dinosaur motifs are there. So, how this is done? Very simple. So, you have this mirror plane of this orientation, you have also a mirror plane of this orientation. So, if you have a starting dinosaur motif here, so after reflection it produces this, and with respect to this mirror plane, this reflection will produce this. Now, this pattern can be translated along this direction A, and it can also be translated along B. So, if this is the distance 2B and this is A by 2B, if it is cos phi. So, if that is the condition that is maintained, you develop this centered rectangular lattice, and where you have this 2 mm is combined with that. So, we call it as C 2 mm. Now, let us come to this P 2 mg. So, this is where which we are still at the rectangular lattice here. So, what you have here? So, in this case I told you that you have a situation where you have a two-fold axisymmetry, you have a mirror plane, and you have also a glide plane here. So, where your mirror plane goes through? So, this is the position of your mirror plane. So, because this after reflection is generated here, this after reflection is generated here. Same way, these two can be related to each other by a mirror plane passing through this orientation here. Same way, if you can also think of, if this is your mirror plane orientation at an orthogonal direction, if you have a guide plane of this orientation. So, then what you can have here is that if this is the this is a repeat distance here, if it is translated half of this distance and then it is reflected. So, what will happen here is that after reflection of these two, this will be generated here, and then it will be translated another half unit, and after reflection along this glide plane, this will be generated here. So, this is the glide plane operation, and this is your mirror plane here. So, if you have a intersection here, if this is the situation here, so then this is the point of emergence of two-fold axis. You see, if this is a dinosaur motif here, if it is rotated 180 degree, this dinosaur will be coming here, and this dinosaur. So, this dinosaur will be coming here, and if it is this position, and this dinosaur will be coming here. So, this particular part where you have the combination of two-fold axisymmetry, mirror and glide plane, that has given rise to a space group, we call it as P 2 mg. And here in this situation, instead of a mirror plane, we now have both the planes are glide planes, and you have also have a two-fold axisymmetry. So, you can understand that these two are related to each other by the presence of a two-fold axisymmetry, and you can think of one glide plane operation, one of this orientation. So, that after translation this is reflected. So, this pair is produced. So, again it is translated along this direction, or after reflection along the glide plane, this pattern produces this here, and in the same way this is also you can think of, this can be translated along this half unit, and after reflection it generates this pattern here. So, there are two guide planes, they are at orthogonal orientation here, and in this case you have a situation as P g. So, P g is lies in the rectangular type rectangular plane lattice. So, where you have very simple. So, if you have this is the orientation of A. So, if this is the translational direction. So, if this is the guide plane here. So, this is just reflected along this and again translated, it comes here. So, this is the way you have this pattern is generated here. You have a single glide plane here. Now, let us come to the hexagonal lattice here. So, under the hexagonal lattice, what you have here is that you have the simple one here is P 6 mm. So, let us consider that in case of 6 mm, you have a 6-fold axial symmetry, that is vertical, and there are a total of 6 mirror planes. They occur in 2 sets, they are 3 in number. So, that is very nicely shown here by this, the orientation of one set of mirror plane, one set of mirror plane, another set of mirror plane, this 3 you can see, and you can also think of another set of mirror plane at an angle of this, that is 30 degree between this. So, you have a very simple situation here of 6 mm, and if this is the primitive lattice here. So, in one node here. So, it is translated along this A, it is also translated along A, and if this angle is 60 degree, it develops this hexagonal plane lattice here. In case of P 6, there is complete absence of mirror plane, you have only simple 6-fold axis of symmetry here. So, what you have here is that if this is the position of 6-fold axis symmetry. So, with a starting dinosaur motif here. So, you rotate 60 degree and it produces the 5 other dinosaur motifs here. And if you now translate along A and you also translate along A and this angle is 60 degree, you generate this entire pattern of hexagonal space lattice here. Now, let us come to this very important operation here. Okay, before we come to this, let us now finish this part here, P 3, primitive 3. So, what you have here? If you have a 3-fold axial symmetry here and if you have a starting dinosaur motif here. So, 120 degree rotation will put this dinosaur here, another 120 degree it will put it here and another 120 degree it will put it here. And if it is translated along A direction, along you can also translate this pattern along and this direction, which is also of the same length A, and if this angle is 60 degree, you generate this pattern here. Now, let us talk about when the 3-fold axial symmetry is combined with vertical mirror planes here. Let us consider this one here. In this case, I have put the red lines as orientation of mirror planes here. So, you see the pattern is generated in such a way that you have a 3-fold axial symmetry here. So, you have a mirror plane here. So, the reflection has produced this a pair here and this is rotated 120 degree, this pair comes here and another 120 degree, this comes here. Now, this is now translated along this direction, that is A distance, and it can also be translated along this direction A. So, if A both the distance is the same A and this is 60 degree, then it generates a pattern which we call it as P 3 1 M. M comes before M. So, when 1 comes after 3 and before M, it means the mirror plane, the vertical mirror plane is essentially parallel to the direction of translation, at least one translational direction, this one or this one, this mirror plane is parallel to the translational direction here. But when 1 comes at the end and we call this space group as 3 M 1, then we see what happens here. Let us see this particular orientation here. Now, the translational this mirror plane is this orientation and this orientation, because in 3 M we now know that there will be 3 mirror planes here. And if we see the orientation of this mirror plane as I have drawn with respect to this direction of translation, particularly if this is A, this is now at orthogonal orientation. When it is a 90 degree orientation, we put the value 1 to the end here. So, P 3 M 1 is this pattern of dinosaur motifs that is generated because of the primitive lattice the hexagonal primitive lattice, which is combined with 3m, and where the translational symmetry, translational direction and the one of the mirror plane directions, they are shown as orthogonal orientation. So, we have done up to this stage the 4 types of plane lattices, that is oblique lattices we have done. We have done rectangular lattices here, we have done centered rectangular lattices here, and then we have also done hexagonal lattices here. So, what is left now? We have the square lattices now. So, we have here the simple one here P 4 mm. So, you can immediately find out this is the position of the vertical 4-fold axis, and this is one plane of symmetry here, another plane is of this orientation. You can also think of another set of mirror plane of this orientation and another set of mirror plane of this orientation. So, this mirror plane and this mirror plane is at an angle of 45 degree. So, but if we talk about the 2 sets of mirror planes, in each set they are 2 in number and each set the angle is 90 degree. That means, if I talk about this set here, this set of mirror plane and this set of mirror plane, this is orthogonal orientation, which you already have studied in 4 mm. Now, you see here that you have a 4-fold axisymmetry. If you generate one pair here and the other 1, 2, 3, this is the total 4 pairs can be very easily generated here. And this can be translated along this direction along vector A, and the distance is A, and you can also translate it in the orthogonal orientation along the same vector A. So, the angle is 90 degree. You essentially generate this square lattice here, but we call this as P 4 mm. In this case of P 4, we do not have any mirror plane. So, if you have a very simple situation here, you have a vertical 4-fold axisymmetry, and if you start with this particular dinosaur here. So, it is rotated 90 degree here, it comes another 90 degree here, another 90 degree here, and it coincides with that. So, this pattern is now translated along this direction here A, and also you can translate it along this direction A, the two are the same, and this is 90 degree, you generate this square lattice here. And in this case, if you have a situation of P 4 G M. So, in this situation here you have 4-fold axisymmetry, and where you have mirror plane has been combined with the glide plane here. So, you see these are the this is what we have called here, this is one orientation of mirror plane we have called. So, you see this is very nicely you can find out this dinosaur and this dinosaur can be related to each other by this mirror plane. These two can be related by this mirror plane here. You can also think of the orientation of this mirror plane, because this dinosaur and this dinosaur they are related by reflection. These and these can also be related to each other by. So, you have this set of mirror planes, they are 2 in number and they are at 90 degree, and this occurs at an angle of 45 degree. So, this is the orientation of a glide plane here, one glide plane here, another glide plane here. So, it translated along this direction, half of this repeat distance of A, and after reflection it comes generate here, and it again translates half of this A by 2, and after reflection it generates this particular here. So, this is a combination of P 4 G M here. So, this is in nutshell the 17 types of 2-dimensional space groups that we have studied, where the 5 plane lattices when combined with 10 planar point groups of symmetry, that has given rise to this 17 types of 2-dimensional space groups. Now, let us consider this particular part in this table. This is summarized here, that the different lattice type and the highest point groups of symmetry as we have done it here, and this is the space group symbols that is there, and this total 17 space groups that we have done. So, this is summarized in this particular table, which I am not repeating here. Now, you also have, apart from translation in a plane, in a 2 dimension, you can also translate into the 3rd dimension here. And this 3rd dimension, how you will translate, what is the angle between the 3rd dimension and with the direction in the horizontal plane, this will now can be combined with the total 32 point groups, and which are there in the 7 crystal systems, or some people call it 6 crystal systems, where trigonal crystal system is clubbed under the hexagonal crystal system, and it produces a 3 dimensional lattices. We call it as space or Bravis lattices here. So, what you have here? You have the combination, we have the convention of A and B and C crystallographic axis we already have considered. So, under this category, under the 7 crystal system, so where we have already are aware of the crystallographic axis and their interaction angles, and the essential symmetry elements which you have already studied. And this 3 dimensional lattices has now been given different names here. Under triclinic, we call it as primitive. In case of monoclinic, we call it as primitive lattice, Bravis lattice, as well as another symbol is used here is C. This is called C face centered lattices here. I will show you why this is called C. In orthorhombic, there are 4 varieties of Bravis lattices. It is called primitive lattice, C face centered lattice, body centered lattice, and face centered lattice here. I will explain this in the next slide here. In case of tetragonal crystal system, there are 2 lattices here. We call it as primitive, and we have call it as body centered here. In case of cubic lattice here, we have a 3 varieties here. We have primitive, body centered, and face centered. And in case of trigonal, we call it as rhombohedral lattice here. And in case of hexagonal, we call it as the simple primitive lattice here. So, let us see what they are. In case of triclinic, the primitive lattice under the triclinic crystal system, you see that lattice nodes lie at the 8 corners here, and I told you since this will be shared with adjacent cells here, each one will have an effective sharing will be 1 by 8. So, if you multiply with the 8 adjacent units here, so what will you have here is equal to 1 by 8 into 8. So, effective in primitive lattice we will have only 1 lattice point here, and this is we call it as primitive triclinic lattice here. In case of monoclinic crystal system, you have a 3 dimensional lattice such as this. This is also primitive, because lattice nodes lie at the 8 corners here, and you also know the angular restriction between A, B and C. So, you know the A angle C beta is not equal to 90 degree, but A angle B and B angle C is equal to 90 degree. Now, you see here in the C face centered lattice here. So, we give a nomenclature here why we call it C face. So, you see what are the situations here? You have the lattice nodes at the 8 corners as we have seen in the primitive lattice, but at the same time we also see the presence of lattice nodes at the center of this face here, and also at the center of this face here, the opposite face to this face here. Now, what is this face? This face is parallel to B crystallographic axis, and this is also parallel to the A crystallographic axis, but it has intersected the C crystallographic axis. This kind of face, which is parallel to A and B crystallographic axis, but has intersected the C crystallographic axis, we call this as C face. When the lattice nodes lies at the center of the C face, then if in the 2 opposite C face it is there, we call it as C face centered lattice, which we see in the monoclinic crystal system here. Now, let us come to the orthorhombic crystal system, where the maximum number of concentration of all the 4 varieties of lattices are present. This is the primitive one, and you remember the orthorhombic, A is not equal to B is not equal to C, and important thing is that alpha is equal to beta is equal to gamma is equal to 90 degree. All the angles between the axis is orthogonal, is 90 degree. So, this is the primitive lattice here, and this is the C face centered lattice under the orthorhombic crystal system, and I define why this is C face centered. So, apart from the lattice nodes at the 8 corners, it also lies at the center of the 2 C faces here, one above and the other below. And this is face centered with a symbol is capital F here. In this case, the lattice nodes lies at the center of all the faces here. So, this is the face, the center of it is here, and the opposite face it is there, and if this is the face here, at the center is here, and this is also at the center here, and this is the frontal face here, that is A face here, this is at the center and opposite to this also there. So, you have this is this in this particular case, you have this kind of situation, we call it as a face centered lattice here. And in this particular case, this is we call it as body centered lattice here. In this case, apart from lattice nodes at the 8 corners, lattice node lies at the center of this unit cell here. When it lies at the center, we call it as the body centered lattice here, and in orthorhombic crystal system, we have a body centered lattice as is shown here. Let us now come to the other remaining Bravis lattices here. So, under the tetragonal crystal system, there are 2 types of Bravis lattices here. One, this is the primitive, this is where all the lattice nodes lie at the 8 corner here, and remember what is tetragonal? The basic requirement here is that along the horizontal plane, this vector A 1 and vector A 2, they are equal in their unit cell lengths here, and their angle is 90 degree, and along the vertical direction, that is C crystallographic axis, this is also oriented at 90 degree to A 1 and A 2, but its unit cell length is unequal or is not equal to with A 1 and A 2 here. In case of tetragonal crystal system, apart from the primitive lattice, you also have a lattice nodes at the center of this unit cell here. When it lies at the center, as we have defined, this is a case of body centered lattice here. So, in tetragonal crystal system, we have a primitive and also we have a body centered Bravis lattice here. In hexagonal system, what we have here? We have this particular unit here, where you have this angle, and this angle is 60 degree, and this vertical direction, this is C crystallographic axis. So, this angle with this direction in the horizontal plane, this is 90 degree, but in the horizontal plane, this axis to axis is 60 degree or is complementary 120 degree. And this is when it if this is the unit cell, and if the lattice nodes are lying at the corners here. So, you call it as, say for example, is the hexagonal, is the primitive lattice here. In case of rhombohedral, this is the situation, this is a rhombohedral shape, where you have the crystallographic axis here is the threefold or Barth 3 axis here. So, you have this corners, 8 corners we can see here. In case of isometric crystal system, you have the 3 types of Bravis lattices here. This is the one which is the primitive lattice. In this case of isometric crystal system, as you already aware that the 3 directions, they are all equal in lengths. That is why we call it as A 1 direction, A 2 direction and A 3 direction, they are all orthogonal, they are in equal in length. So, A 1 is equal to A 2 is equal to A 3, and this is the primitive variety of the lattice and the Bravis lattice. in the isometric crystal system, and this is the face centered lattice in the isometric system here. So, the lattice nodes lies at the center of all the faces here, and in case of isometric crystal system, you also have a body centered lattice here, where the lattice nodes are at the center of this particular crystal here. So, this varieties, if you have this 14 types of Bravis lattices that we have seen here, this 14 Bravis lattices now can be combined with 32 point groups of symmetry to generate a total of 230 space groups here. So, with this we more or less end this particular part of translational symmetry here, and with this we end this particular part of the point group of symmetry, translational symmetry and their combinations and generations of 2-dimensional space groups and 3-dimensional space groups. We call it as Bravis lattices here. So, Bravis lattices and the 3-dimensional space groups, and this a total of 230 space groups that can be generated because of the combination of 14 types of Bravis lattices with the 32 point groups here. With this, I come to an end to this lecture. So, in the next lecture, we will move forward and will discuss how the symmetry of the crystals can be given a nomenclature, particularly the faces, how they can be given a name, and at the same time the directions in a crystal, how they can be given a name. So, in the next lecture, we will discuss about the nomenclature about the crystal face and crystal direction here. Thank you.